start, and I think the good point to start is an introduction. Could you please introduce yourself?
Yes, so hello everyone. I'm Niccolo Somaschi, and I'm a co-founder, president, and CTO of Quandela, which is a startup created in July 2017, based on a technology part of the National Research Center of France. So we are a French-based startup located near Paris, and we work on photonics and quantum technologies for quantum optics, mostly application.
Yeah, and could you maybe talk a bit more about the technology, what exactly you're working on? Like, what is the main piece of the technology?
Yes, of course. The company started spinning out a technology based on semiconductors, which are manipulated to develop efficient sources of quantum light, which means emitters of photons, single photons, and indistinguishable, identical photons. So the entire principle of this technology is to use nanocrystal, which you can grow in semiconductor foundries, and include them in optical cavities, so to efficiently collect the emitted single photons. Basically, what is important in this technology is that this nanocrystal behave as artificial atom, which means they can emit only one photon per time. And that's the entire principle of having this semiconductor structure.
Yeah, and looking at this, let's say, structure, it's already a product, right? You started with this idea, and then you move it to a product, right?
Yes. The way it started actually is we have to go back to 20 years ago, when this material started to be recognized and discovered in laboratories near Paris, actually, and at the same time in the United States, and people realized afterwards that these nanocrystals were efficient sources of single photons. The problem then was to actually collect them, so to manage to make this single photon escape from the semiconductor. It's a hard job if you think that LEDs has a very low brightness, so very low emission efficiency, because of course the light is stuck into the solid state material. So 10 years after that were devoted to develop a specific structure that will allow to extract the photons from the semiconductor and actually to use it. And when I joined the group of Pascal Senelar in the CNRS in 2013, as a postdoc, we worked on these devices, and in 2 years work, we managed to achieve performances that made them actually helpful for the community to speed up and increase the computation power of their protocols. So people started to ask to use this device because it would allow them to explore new regime that they couldn't do, and the experiments they couldn't done if they were using still the previous technology, which is based on lasers. So the product then, it was basically almost there. It was a prototype. It was a device fabricated in the lab, and the company was created in order to help these people in the research community to actually have these devices and use them to do their research. And that's from when we started.
Yeah, so if I understand you correctly, it was first a request from the market, let's say from the research laboratories, and then you thought, okay, it will be interesting to move this technology into real products.
Exactly. So we created like this. We had already requests from prospect client that in the 4 past years became actually our clients. And of course, we put a lot of effort in making these devices usable and more robust and more easy to manipulate by non-experts. So by people which develop other parts of quantum technologies and not directly solid-state systems.
Yeah, actually, I think it's very important question that one thing is to develop, let's say, one prototype in a lab, and another thing is to develop a real product which will be used by people who don't know much about this. So how did you deal with that in the sense that you have to do really a decent product which will robustly work for years, right?
Yes, it's very tough. So we had a lot of mentorship from experienced people who already developed their companies spinning off technologies from their lab. So we were lucky for this. And the way it started was basically by removing pieces from the actual setup that we have in the research lab, try to make it more compact, more stable, and especially to write procedure that for us were normal and standard, but try to make them as a set of bullet points so that we could ask other colleagues of nearby labs as a game to come and try to use the prototype by following the operating manual that we have developed. And there we learn a lot because we really understood what was the missing link that or the parts of the prototype that we had to improve in order to make it more user friendly.
Yeah, and the main part that this product, the main goal is to deliver a single photons, right?
Yes, is to exactly deliver a high stream of single photons so that every time you press a button, you know that you have a single photon in your optical pulse. And this is because mostly now these devices are used in optical quantum computing. You want many of these photons in order to interfere them in optical circuit, so to develop complex operations. So of course, the power of your computation depends on the number of photons at your disposal. So of course, you need a very high number.
Yeah, and I might be mistaken, but I think people were looking for a single photon source for quite a while. So it was an advanced in your laboratory, or it just happens that just in the community people realize that new technology is coming. So how you develop this?
It was part of environment of the community, of course. So there are many other research groups that were working on this. The key point in the technology developed in our lab is that it was developed 10 years before a specific processing step, so clean room step, which allow a high yield of fabrication. While the other research lab were fabricating devices and only few of them were working over 10,000, so means that there was a lot of inefficient steps there in the fabrication. We could fabricate 40 and have 15 that they were working properly. And that's what put us in an advantage compared to other people.
Yeah, and the photon source is an application for something else, right? Because as you said, it's for quantum computing. So who's, let's say, a main customers who are interested in buying the single photon sources nowadays?
So at the moment, our customers are mostly research labs, academics. We have also a private research lab. It's a startup that is working with us since the past October. And there are research labs which are developing optical quantum computing platforms. So plugging these single photon sources into integrated circuits, which actually develop the computation task and then analyze and activate the logic gates on the circuit itself. But there are many other applications for quantum-like sources, and the first one is communication. Communication can only be done by light, and single photon are part of some protocols, although at the moment laser system work very well with just QKD based protocol where information is transferred from one point A to point B. but more complex systems are actually required to develop networks where entanglement will be required, where teleportation will be the core part of a large network with many points.
Yeah, and you mentioned quantum computing and quantum network, and this nowadays very buzzwords. So the whole community seems a bit hyped about that. So I really want to ask you, what do you think? And there are different approaches to attack the problem of quantum computing, and among others is photonics. So what do you think is the most promising candidate to become a quantum computer? I can mention neutral atoms, ions. I know that it's like $1 million questions, but what do you think is really the most promising candidate for that?
Seeing how the things are advancing in the past year and a half, I would say that most probably we will have many different platforms, and some of them will be optimized for some specific task. For example, some machine will be ideal for simulation, some others for long-term fault-tolerant quantum computation, but there could be also other platform that will solve this noisy intermediate scale application because they are easy to implement, and they probably would work already in this kind of regime.
And what do you think is the advantage of the photonic platform compared to others?
The main point in favor of photonic platform is the fact that by nature, this machine will be interconnected. We are realizing in the community, especially with superconducting qubits, that when you want to go to many qubits, thousands and millions, you need also large infrastructure, large cryostats. And this sometimes, people are starting to realize that it can be a really big issue. So parallel computing will be a real game-changing to go to many qubits, but only few platforms are actually very prone into be interconnected by photons. And photonic, of course, is the most efficient one in this sense. So you can imagine different machine interconnected, and the computing, the calculation is actually parallelized on different of them, which allows to scale up the computation power, but still manage the fabrication and the material issue on a small scale instead of just making a huge quantum machine in one piece.
Yeah. So the single photon source, it will be, let's say, a part of the quantum computer system, right?
Yes, indeed.
And what is, let's say, the other parts which and what is the development in other departments? Because if you're talking about quantum computing, you want to put all pieces together and then eventually do the quantum computation, right?
Yes. So I like to say all the time that quantum optics and optical quantum computing is a bit of DIY, like do it yourself, in the sense that being naturally interconnected, so you can connect modules by optical fiber, which is the natural wiring. Many people had focus on their expertise. For example, we focus and other startups focus on the quantum light generation. Some other people focus on the development of integrated circuits with silicon-based materials, so you can fabricate micrometer scale components on of semiconductor chips. And this is the second part, the part which actually allows the photon to interact and makes the actual computation. And the last part is detection. Single photon detectors, which look at the statistic of your calculation and gives you basically the answer of your computation, is a technology that is already commercially available since the past 5 years, developed by other startups that were developed from proprietary technologies of academic laboratories. These are the three main hardware components, and of course you need the other levels for controlling the circuit, so software, an algorithm, a protocol, and of course a platform where you can control your hardware system based on your parameters of the protocol.
Yeah, maybe can you say something? What's the power of photonic quantum computer? Because everybody is interested how many qubits, everybody is running around and thinking, okay, how many qubits this platform has, what type of depths you can execute, what type of circuit you can execute. So could you say something about what is the number of qubits in the photonic platform and what type of circuits we can execute, in terms of gates?
Yes, that's a good point. For whatever it means, I want to refer to the latest advances, where actually a Chinese group managed to reach quantum advantage with a photonic platform after Google last year managed to achieve quantum advantage with the superconducting qubit platform. And these so far are the only two platforms among the others, among the ion trap and the cold atoms, to have reached this milestone, which means that there is a lot to go and there is a lot of potential in the technology. So far, other platforms based on photons have shown tens of qubits. Yeah. And that's actually where we want to go, to start to provide an easy reconfigurable platform for users, so you can actually directly operate physical qubits. And this can be done with the modular approach by plugging in source devices with integrated circuits and detector. What's the important thing about optical quantum computing is that respect to the other platform, the qubits are flying qubits. They are not stationary qubits. So the standard way we see the computation, for example, with ion trap or superconducting qubits, is not the same. We don't operate two qubit gates in deterministic fashion because optics behave with a probabilistic way. So the two qubit gates is actually something which is not efficient, but there are other paradigms in the computation, like measurement-based quantum computing, which will allow to explore the power of photonics in a different system, a different way, as compared to the other platforms.
Yeah, and of course, it's another $1 million question. When do you think that the quantum computer will address the practical issues, right? Because of course, quantum computing is a very nice thing by itself, but what most of the people want is to really solve a real world problem, right? So do you think we're getting close, or we're still far away?
Well, we see every few months major breakthrough from companies and research labs. So I really think that maybe a few platforms will be able to reach the hundreds not corrected qubits in a couple of years or so. And this is recognized as a lower bound limit in order to really have practical application, like for drugs design and molecule design and so forth.
Yeah, and actually, do you, let's say, somehow compare, let's say, photonic platform to other platforms, or you just focus on producing your job really nicely, or you sometimes looking, okay, what other people are doing, how many qubits do they have, or you just focus on what you're doing?
Well, of course, we look around, and personally, I'm very curious to see how the community is advancing. I'm actually a scientist as a base, so whatever comes out, it gets me super excited. So I don't see it as space race, like other people say. I really love to enjoy, and I'm excited to learn when someone reaches something that even as we are not there yet. Of course, I will be more excited when we will reach it too. But that's on our shoulder, and that's our job.
Yeah, that's true. I actually want to go to a different thread in our discussion about the company. Could you say a bit of the company, how you decided to found the company? Because lots of people in different labs are thinking that one day maybe the technology should become a product. And what's your story? How you decided to do this?
As I started to explain before, it was not in my plan to create a startup in quantum technology. I ended up being working as a postdoc in this laboratory because I always wanted to look and work on this technology, which it came out working too well, probably. And that what made us surprised was really the community that was approaching my supervisor at the time and now colleague in the startup, asking to use this device. So it was really the community demanding and showing the needs of this kind of object. And the point was that the research laboratory was not a fabrication facility. It was a research laboratory to do research. And they couldn't focus on just producing these devices for the community. So I just said, okay, why not we sell it? We create a structure company on the side, which will focus on the reproducibility and improving the performances. So the group will continue to research. And that's how it started. So I was in my postdoc ready to change job and maybe do something completely different. And as you may say, you was there and the good time and the good moment, and I just took the ball, and so far is going well, and it's extremely fun.
Yeah, it sounds it's a very good story. It sounds really good. And how many people like joined in the beginning?
At the beginning, we were 3 co-founders, and we started hiring a PhD student that I want to thank because she jumped on this crazy project very bravely, and now she's actually an employee of the company. And from then, now after 3.5 years, we are 15. So it's not a huge scale up because we didn't need and we didn't want to raise money from the beginning, as most of the startups in this domain do, because we had subsidies and we had clients, so we were able to proceed in a good speed without external private investors. And only last summer, we decided to start working with some investor in order to develop new projects, which at that moment require extra funding.
Yeah, but you didn't take, let's say, a scientific grant to start with. You really start with the technology which was available in the lab, right?
We had some subsidies, national subsidies. We had the European grant, and then another European grant which provided the funding for a PhD student. But mostly going through national French projects, deep tech projects and startup projects, we managed to continue and grow enough to make sure, especially us and the founding team, the manager team, to be sure on the path that we want to take and the way we want to structure the company.
And you mentioned that right now it's 15 people, and these people have a scientific background, or it's already more like engineers or something like that?
They are mostly with a scientific background, but we are starting now to look for different profiles. For example, electrical engineer or expert in cryogenics, and pure theoreticians or computer science people, which may have or not direct directly working with quantum related stuff.
And let's say, to understand the product, do you have to have a PhD or master degree, or it's possible to explain the basic to, let's say, electrical engineer?
Our job is now to, and we are almost there, to provide to clients closed boxes which contain either cryogenic or laser optics or other filters and stuff, but they can be easily managed even with the standard engineering background.
Yeah, and let's say another question which sometimes people ask is, when you're hiring a new person, what type of skills you're looking for and what type of background you're looking for?
We have realized that the skills are important, but most of the time more important the personality and the social skills. We're always looking for people and profile that fits well in the company, because people can get trained and learn fast, but if there are issues in the personality, that's much harder to solve. So we look first at that, and even in all this complicated period of pandemic, we want and we meet every time the people that we want to hire in person, and we spend time with them, and we let them spend time with the team. So this is mostly that's one of the most important points we look at, and of course also the passion in the stuff we do, and we try to see if these people are curious and want to participate in the adventure with actually their passion. That's what makes it important and more efficient also on the daily basis.
Yeah, I agree. I think people with passion, they really work harder and smarter. So I feel it's really important. And what do you think is the main challenge when you're looking backwards? What was the main challenge in funding the company?
The beginning, clearly jumping from academia and a postdoc researcher and being forced to manage completely different things in the daily life. That was one of the hardest part, at least for me. For example, managing finance or bureaucratic issues or administrative issues with the patent and lawyers, or learn how to interact with clients, because that's a different thing. You can discuss with your collaborators all around the world and share science, but then when they pass on the other side and you want to try to show them that your technology can actually help them, so you have this client perspective, everything is different. So this is also not easy to adjust to.
Yeah, I think lots of people experience that fear, you know, when you go from academia to, let's say, startups or industry, that now it's a different field, that it's definitely a fear. And how did you overcome this fear? You just decided to push through anyway?
Yeah, of course, you wake up every day for some months and you ask yourself, what the hell are you doing? Yeah, am I totally crazy or just completely mad?
Yeah.
The answer is yes, but then, as I said, when you share the working environment with other people, your co-founders, which have the same passion, you forget about this. And of course, you believe in the technology you are developing when you create the company. But really the passion and the fun you can have every day in the lab, that makes it all.
Yeah. And what's your plan for the future in terms of what's your plan for the company in, let's say, for the next 5 years or 10 years? So what are you going to do? What other products you're going to deliver?
So we want to focus on the on the commercial side, so we'll not stop providing devices and optical modules which will be more optimized and easy to use for the community, so to help the community advancing. But we started to focus on a development internally at Quandela of an optical quantum computing platform. So that's where my attention will be mostly focused, and also with the development of a quantum algorithm team, which will focus on practical implementation, a useful implementation of protocols using tens of optical qubit. So that's where we will focus in the next 5 years.
And you want to, let's say, assemble a full stack quantum computer just with Quandela, or you want to get in touch with other companies?
We will clearly, as I said before, work with other companies which are the best doing other parts of the platform. For example, circuits and detectors is something that we want to keep in Europe. So we are focusing, collaborating, working with European startup, and of course that the hardware is one part, but of course there is a big challenge in the other layers that we will develop internally, both in the compilation, so in the activation of the hardware part, and in the software and algorithms.
Yeah, and if I understand you correctly, the full point for the community or for your collaborators is to assemble the full stack quantum computer based on the photonics.
Yes, we will not develop a fault-tolerant quantum computer. We will start with tens of qubits, which are easy to operate, so they will be available for users, companies, or other researchers who want physical qubits to operate, and we want to do it fast because this is missing now in the community, and then focus on reaching noise intermediate scale level.
Yeah, and what do you think is a showstopper right now? What's like the main bottleneck to proceed faster, to build these hundreds of qubits and execute circuits? What's stopping the community and the technology?
On the photonic side, we have major bottleneck, as I was saying before, in the probabilistic approach of the gates. So a strong focus will be on developing protocols which uses other schemes, for example, measurement-based quantum computing by using cluster state of entangled photon instead of directly going in the so-called circuit model. And this is a big challenge both on the experimental side, but also on the theory side, in order to adapt this concept to a useful and low resources practical implementation. So it's really a lot of work on the architecture.
Yeah, and you mentioned quantum computing based on photonics, and I think it's a very cool goal. I really wish you luck to achieve that. I really want to see quantum computers soon. I really want to do that. And do you know if other people pursuing that, or like do you have like collaborators, or sort of like if other people really doing the same things or trying to approach with the photonics?
Yeah, there are several startups in Europe, and actually we are not alone. We are in good company. We have one startup in Denmark fabricating single-photon sources, another one in UK, then another one in UK which is developing a modular optical quantum computer. It's called Orca Computing, and of course we discuss a lot with them. There is a startup in the Netherlands which is fabricating one of the most efficient integrated circuits, which is called QX. And of course, and these, I think they are more related to the quantum computing side. And then there are others like the ones that fabricate detectors that provide the best detectors and just focus on selling this key enabling technology without making any platform like what we're trying to do.
Yeah, and of course, right now we focused on quantum computing, but there are other goals, right? We can use this photonic source, a single photon source for other applications. It just probably quantum computing is the biggest and the noisiest in the field, right?
Yes, yes, indeed. We have projects with the region in France, region in France, which is the region around Paris, where we start to develop sources in telecom wavelength for developing a practical network connecting parts of Paris to other hubs on the south suburbs.
Yeah, seems nice, and it was very nice talking to you. It was really a pleasure, and I want to wish you luck with your development, because I really want to see quantum computing. I don't even care on which platform it will be based, but I just want to do some computation on that. I think it's a very important goal.
Thanks a lot.